Hello, everybody. Thank you and welcome to the webinar organized by Imagine Optic and Axial Optics. It's today the fourth webinar dedicated to our offer in terms of Wavefront Sensing and adaptive optics. I hope everybody is comfortable, hear us correctly. I think we can go ahead with the agenda. Oh, with the presentation of Axial Optics, which is our partner and distributor in the US. We are located in San Francisco, Sacramento, Los Angeles, and Boston. We are specializing in the sales and technical support of optical instrumentation for microscopy, laser beam diagnostic, optical metrology, and of course, wavefront sensing and adaptive optics. So Imagine Optic is a European pioneer leader in innovation dedicated to wavefront sensing for optical metrology, laser beam diagnostic, and adaptive optics. The company supports a broad range of wavefront sensor metrology system, providing high performance measurements, wavefront measurement from the X-rays to the SWIR. We are also specializing in adaptive optics for life sciences and laser, with two proprietary technologies of deformable mirror and software platform compatible with any deformable mirror from the market. Imagine Optic is also an engineering service provider, this to meet with custom requirement, custom projects. Today, the agenda, my colleague will introduce a new feature that is now available for the HASO4 broadband. So we will come back onto the specifics regarding the HASO4 broadband, and we will introduce this new feature called the SpotTracker and a new software version that will come with that wavefront sensor with Waveview 4 and its SDK. We are then going to go with a live demo and a session dedicated to question and answer after the closing remarks. Guillaume Dovillaire, that's your turn.
Yeah. Hi, everyone. Hello. I'm Guillaume Dovillaire. I'm the technical manager of Imagine Optic.
And I'm Patrick Sheen. I'm the Chief Digital Officer at Imagine. So we're gonna start this conversation with our masks, obviously. Yeah. And I'll then move away to leave Guillaume to the demonstration and in a more comfortable setting. Yeah. But just to summarize things, Guillaume, what's the general theme of today's presentation?
Yeah, we'll see today two main innovations in terms of wavefront sensing. The first one is a new software, Waveview 4, which is, I think you'll see that, a quite revolution in wavefront sensing. And it will be also an opportunity for us to introduce the SpotTracker technology. This technology allows to simplify a lot the way you will use the sensors in order to measure the wavefront you want to see, you want to measure in your optical system.
Quite an exciting program. So I'll leave to that.
Yeah. So we'll just see some few slides before switching back to the demo. I'm now allowed to remove my mask. So if some of you didn't know me, here's my face. So let's focus a bit on the sensor you'll see today. It's a HASO4 broadband. Its name is quite clear. That means that this sensor is a broadband wavefront sensor. Its range in wavelengths starts from 350 nanometers to 1100 nanometers. What you have to keep in mind is that its absolute accuracy of lambda over 100 root mean square is ensured in this entire range. This sensor is quite small. It's very robust, easy to mount. You see this on the video. and as all the range of HASO4 and basically Shark-Hartman technology is insensitive to vibrations, and you can get rid of air turbulence in the room only by averaging. You don't have any problem with blurred fringes or things like that. I want to focus also on the fact that there are many other techniques existing to measure wavefront. Each time these new techniques are compared to Shark-Hartman technique because it is still a golden standard in terms of wavefront sensing. You'll see today on the demo that now Shark-Hartman sensors are very, very easy to use as you don't have to align it anymore. And as this technology allows you to measure wavefront and intensity maps simultaneously, you can calculate many of the parameters in the beam, such as length square, point spread function, modulation transfer function, and you'll have all these diagnostic live. Another interesting thing about this technology is that it's very sensitive to light. Only 8 picojoule per image is needed to do the measurement. So for instance, if your exposure duration is 10 milliseconds, you need only 1 nanowatt to use to do a measurement, 1 nanowatt, which is quite small. This sensor, as it is brand new, we did a lot of work about mechanics. On mechanics, it is compatible with many other products in our catalog, such as the Orflex 2 and the large aperture beam expanders. Maybe some of you attended the webinar we did in April about these two products. I think Patrick can confirm that this video is still online.
It is.
Yeah,
absolutely. You can watch it on our YouTube channel.
Perfect. Thank you. Well, let's focus a bit more on SpotTracker because we announced that it's quite a small revolution. In order to in order to present you this, I have to, sorry for that, explain you how works a Shark-Hartman sensor. So let's go enter into a bit more details. I don't know why. Yes, it's updated. So Shark-Hartman sensor is based on the association of a microlenses array and a detector. We have here in green the microlenses array and the detector itself, so it can be a CMOS or a CCD camera, whatever. If you imagine wavefront coming here, each microlens will create a spot on the detector. If here's wavefront is not perfectly flat, the spot which was in the axis of the microlens will be shifted because of a small local slope here in the wavefront. So in a Shark-Hartman sensor, the camera signal you acquire from the camera is not an image, but is an array of spots. And by calculating all the position of these spots, in fact, you're measuring the wavefront slopes. And as you know, the wavefront slopes, you measure the wavefront derivatives, you just have to integrate this data in order to retrieve the wavefront here. So the problem of many wavefront sensors, including Shark-Hartman wavefront sensors, is this problem. The problem is coming from the fact that, as just before I presented, if you imagine a flat wavefront coming onto microlenses, you have a regular array of spots, okay? If you imagine a tilt, and this tilt corresponds to the fact that the flux passing through this microlens is not focused here, but here on the axis of another macrolens. What happened in that case? The problem is that in the camera signal, you still have an array of spots. But if you enter into the computer and say, okay, now I'm acquiring this image, how can I distinguish which spot corresponds to which microlens? And in order to remove the problem, all the wavefront sensors, and not only Shark-Hartman sensors, need the sensor to be pre-aligned onto the beam. That is why even on our previous and our older wavefront sensors, we added pinholes and features. Maybe some of you already use our software We call this feature trimmer, new lens, strange button in the interface. And all this disappear because we found a way to automatically detect which spot corresponds to which macrolens. And this feature allows the user to have only the measurement of the wavefront in head and not how to align the sensor. Because at the end, the user do not have to pre-align the sensor. They just put the sensor in the beam and it measures. The software automatically detects the spots must be associated with each macrolens. And this feature, I can't tell you all the details because some of these are secrets, but it's basically an association of a very specific macrolenses array and a software feature that is included in our new release of Waveview. There is now no dot at all on the display tilt. There is no risk of subtraction of any calibration or reference with a shift, and there is no impact on the calculation frequency.
So, if I understand correctly, it's like there's an expert aligning the wavefront sensor with a beam or some kind of a magic trick to.
Yeah, it's maybe some of you already use a HASO interferometer. It's like if you put the optics in the beam and the HASO automatically find the fringe because it has the dynamic enough just to measure the fringe, to find the fringes and measure the wave. It's exactly the same. It's like you have an expert saying, okay, I just put the sensor, and the expert allows you to be very confident on the displayed wavefront without any thinkings on how to align the sensor. So it's quite a revolution, we think.
Pretty impressive, pretty cool. And so I understand this is part of the new Waveview 4 software release.
Yeah. In fact, we included this feature in the new Waveview 4. And as I said in introduction, we think also that it's quite a very big change in terms of wavefront sensing. In order to present you this software, just a small reminder of where we were in 1999 when our first wavefront sensor was manufactured. We used this software HASO V1. It has the same name than the sensor at this time. It was written in C and LabVIEW. Basically, wavefront sensing software is software with a hardware interface with a camera, and we use for that the camera manufacturer SDK just to acquire the images. We have just then to calculate the centroid, the position of the spots, and then the wavefront local slopes, and then the wavefront itself by 2D integration. And of course, as we have this information, the software display all the possible diagnostics. In 2002, we switched to this new layout. We included Zenki Projection. We have the compatibility with many other cameras because we had at this time many different wavefront sensors to propose to our customer. Still C and LabVIEW, and then 2009, probably some of you already saw this software because it was very common this in let's say maybe 10 years. It was written in C++, LabVIEW, more dynamic, faster. It was quite a nice release. And then in 2016, we changed the name of our software, appears the name Waveview now. And we have also changed completely the core calculation in C++. We use at this time core 4, and it's still a LabVIEW interface. And now it's the opportunity for me today in 2020 to present a complete new layout of what is the future of wavefront sensing software. So this is what you see in a demo in a few minutes now. So as you see, it's a completely modern interface with all the parameter trees here and many diagnostics you'll see here in a common window. And it's now written completely in C++ and Qt.
Well, thanks much, Guillaume. Very good looking. Just a quick question. So You're going to demonstrate some of the new functionalities of Waveview 4 in a minute. But I understand there's also an evolution in the software development kit in the SDK.
Yeah, because as we are now entirely compatible in C++ and Qt, we updated the SDK. So its name is Webkit. It's basically SDK. We propose this in 4 different languages. Here are 2 examples of how it is written in C on the left and in Python on the right bottom. This SDK is very nice because a lot of application now needs the function of wavefront measurement to be included in a more complex machine or more complex optical bench. And it's now very easy just to call a function in our SDK just to say, okay, init camera, grab an image, calculate slope, calculate Zenki, and then you have the entire diagnostic in your own application in your favorite language. So this is something new we proposed today. I think most of you will appreciate to have so well written SDK now.
Well, thanks much for the overview. And maybe it's time for us to jump into the live demo.
Yeah, before this demo, I just want to show you this picture. As you see, it was very nice weather yesterday morning in Paris. Autumn is quite here. And just to present you the 5 main people in our software development team, Maher, Bruno, Nicolas, Pauline, and Jerome, I want especially to thank them because thanks to their work, we are now able to offer to our customers this revolution in terms of wavefront sensing software. But now it's time to go to the demo, I think. So here's a live demo. Please, Patrick, can you just
do that?
Yeah, increase the camera. Okay, thank you. I'm now visible in big. So here's the bench I want to use today. As you see, it's an empty bench. It's an empty bench. You sure, Patrick, that I want to see that? No? Okay. Let's stay in this configuration. So I hope you'll see this bench now. So there is a sensor here. It's a Shack-Hartmann Wavefront sensor, HASO4 BroadBand. Maybe I can just put it closer to the camera so you see the sensor. It's a quite nice design. So the camera is here, the micro lenses are inside. It's a USB 3 connection, and it has quite a smart mechanical interface with 3 isostatic points. So you can just put this here, it's a magnetic one. So it's very easy to set this on the stage. And here you can maybe see what we call a SMLS. It's a standard product from our catalog. It's basically a laser diode which is fibered in a single mode fiber here, and this single mode fiber comes to the bench here through a holder visible here. So I just have a single mode fiber and wavefront sensor without any optics in between. The expected beam at the output of this fiber is a Gaussian in terms of intensity and is a sphere in terms of wavefront. I use here a source at 520 nanometers. It's a red one, green one, probably see on the camera. So it's quite an intense here because I have to reduce exposure duration of the sensor below 30 microseconds, so very short exposure duration, because we have a lot of light here in order to see me through the camera. I have also in the bench a lens. I will use this lens at the end of this demo just to show you how we can easily collimate a beam because I have point source here. If I put this point on a focal plane of this lens, I will create a collimated beam which will be measured by the wavefront sensor. Okay, for that, I will now take the control of this webinar by sharing my screen. So you probably see now just a folder where Waveview can be run. So I just have to double click on this in order to open the software. Here is the software. As you see, because I prepared this demo, the software automatically detected the Wavefront sensor connected, which is the serial number 4795. So it is automatically connected. I have here a part of this software dedicated to parameters. And here on the left, I can start the camera, grabbing and stop it. I have other features to acquire images in a different way. And on the right part here, I can open many dynamic windows. This part here is dedicated mainly to files, saving files, opening files, adding mask. I will show you this in the demo. And this is a new part on our software dedicated to configuration of the custom configuration of the layout. And you'll see this in a few minutes. But just to start, I will just start grabbing and open. What is done first is the camera signal. So here is the signal coming from the Shackleton sensor. If I just put my finger in the beam, you can see that it's live. The beam disappears when my finger is in the beam. So maybe some of you know how a Shackleton sensor works, but okay, here are all the spots coming from all microlenses. If you don't like these colors, I can easily switch to grayscale here. What I can do too is deactivate the scale automatic and set here this value to 300. All the pixels which are above 300 digital numbers will appear in white. It's a way here to see that diffraction of each microlens, which is square, creates sync square function in the detector. And you can see here the sync square shape. And as you see now, maybe things are changing here because the camera noise creates, of course, noise in the image, which is fine. And as I said, the purpose of Shackleton algorithm is to calculate the centroid of all these spots. If I display the centroid, I can just use this way. It's an array of vectors. I can just increase the size here of this window, increase the size of the vectors because all these vectors are very small. As you see here, the vectors, I can zoom again in order to zoom on all the small vectors. Things are changing due to camera noise, but also the air, which is here in the room. I create heat, so I create turbulences. By just averaging images is quite very easy to get rid of this noise. This is one clear advantage of Shackleton sensing. So this is a way to display the wavefront derivatives. You have just to now integrate the data in order to display the wavefront, which is here. Let's switch off now a little some images. So on this wavefront, I can just zoom here on the root mean square. As you see, it's 8-9 nanometers here. And I have to change the configuration a bit because I see that here I'm not exactly set up as I wanted. Here it is. And I can also zoom here on the PV. So I have here in this window a zoom of the values of the PV of the wavefront and the root mean square of the wavefront, 6 nanometers. And what I can do now is just opening the last window I wanted to show you. It's the beam parameter. The beam parameter window allows you to see the tilt of the incoming wavefront, the curvature, so the inverse of the radius of curvature of the wavefront, which is displayed here. So here, clearly, the distance between the source point at the output of the fiber and the wavefront sensor is 520 millimeters. And we are able also to calculate the focal point position in X and Y because we are measuring tilt and curvature, so it's very easy to calculate the center of this sphere. Now, what happens if I adjust tilt the wavefront sensor? I just here have a hand on the sensor, just add some tilt. If I tilt the sensor, so you can easily see the spot moving. So now we can maybe understand what happened because of this spot association problem, because this image is exactly the same as this one. So it's a problem for the Schackertmann sensor to know which spot corresponds to which microLED. But here, if I just have a look here and zoom on the tilt X, you'll see that I can just add tilt 30, 40, 60, 100 of milliradian. No problem of association of microlens with spots. I can even do more. I can hide the image, change completely the sensor orientation, reopen the image, and automatically the tilt is now measured as minus 150 milliradian. It was plus 150 milliradian. So without following any spot, the sensor is able to detect which spot corresponds to which microlens. This is quite magical, and it changes everything in the way you use this wavefront sensor. So now what happened on the wavefront with such a big tilt? I can just redo the same here. For instance, 100 and let's say 100 milliradian, roughly. Let's have a look on the wavefront. As you see, wavefront root mean square, 5, 6 nanometers, lambda over 100, and the entire square pupil. In fact, here what is displayed here is not the absolute wavefront measured by the wavefront sensor, because here in this part, I filter the component of tilt X, tilt Y, and curvature, because in this configuration, the tilt is huge. If I unfilter the tilt and curvature, the PV of the wavefront is now 650 microns. So the optical path difference is now 650 microns. So it's more than 1,000 fringes in an interferometer. But besides this huge aberration, if I filter it, the Schackertmann still continue to measure the wavefront with an accuracy of 5 nanometers. So this is quite interesting to show you this, because Schackertmann sensors are always famous for their dynamic. They are a lot of time chosen because the amount of aberration is too big for interferometer. Keep in mind that the accuracy of the sensor remains very, very good, better than lambda 100, even if you have 1,000 fringes in your aberration. What I can do also is I can just click here just to reduce the auto scale on the camera signal. What I can do now is just to change the distance between the fiber and the wavefront sensor. There it is. Oh, I have now problem, because here the software say, okay, saturation problem. Of course, I have too much flux on the sensor. I can just reduce the power of the source in order to retrieve the saturation, which is in the range 70%. I just moved the sensor. I didn't align it at all. Still 4 nanometers of error. Maybe I can do more and just decrease the distance between the source and the wavefront sensor up to its minimum. We have a lot of saturation, and even you can see blooming in the camera because the camera saturates a lot, so I have to reduce the flux here. Let's come back to 70%, for instance, and still 4-5 nanometers. And here in this configuration, if I look at the raw wavefront, which is quiet now, we have PV, 260 micron of aberration, not only tilt, but curvature. And I can do maybe more if I just continue to tilt the sensor in order to, let's go up to 100, 1000 PV. Let's go, what happened in that case? Okay, I have 1 millimeter of optical path difference. If I just filter this, what is the residual? It is, okay, I don't have 5 or 6 nanometers, I have now 10. As you see, there is maybe a small error here, but if I just open the intensity profile, you see that it's a coincidence with the fact that there is not a lot of light here. If I just translate the sensor in order to retrieve a bit more light, sorry for that, here it is. We still have 6 nanometers, 5 nanometers of wavefront error. I think it's quite interesting an interesting feature here I can show you. Keep in mind that in that configuration, the sensor is in the worst configuration we can imagine. You have a huge tilt, 70 milliradian, a very big curvature, and the intensity profile is not flat. So it's the worst case for a wavefront sensor. And this one still have the accuracy of 5-6 nanometers within square. Maybe a small zoom on what we can do with this software here. As I said, there is a lot of parameters here you can change. And because there are too many parameters, for instance, error function, double pass configuration, it's quite very easy just to say, okay, I want to select some of these parameters as a favorite. If you select this, the parameter comes here, and you have now all your preferred parameters that are displayed here. So you can select from all these the best parameter you want to change daily in order not to have to find everywhere the parameter you want to change. So it's quite an interesting feature here. What I can show you too is, yeah. I can, yes, maybe stop here. Yeah, and then if you want to save this layout here, it's very easy. You save the layout by saying, okay, it's mine too. And if you reopen tomorrow the software and select here mine too, you'll have exactly the same layout in the software. So you'll be able to see the wavefront with the same parameters, with the same everything exactly with the same appearance here. I didn't show you, but I can change here the color of this. It is also possible to see this in 3 dimensions if you prefer 3D. If you want to print this, to include this in your report, it's very easy. You print, in fact, it's not printing on a real printer, just save it as an image. I think it's a PNG format. If you're interested in looking at the raw data of this wavefront, you can, for instance, save as text. So it's an ASCII tabulated format. You can reopen this in Excel or the language you use usually to treat your data. What I can do now is just restart the acquisition and just move back the sensor from the source, put it somewhere here. So the flux now is a bit small, the saturation is only 5%. Can just increase the source power to retrieve again a measurement of an image which is not saturated, let's say around 70%. I talked to you just before about the lens I have here. I can just try to put the lens in the beam. I can just show you this and put here the lens. As you see, the lens is here. It appears I have an iris here. can just close it a little in order not to have a too large wavefront. Things are blinking here because we have a lot of saturation. I added the lens in the beam. I have to reduce the power of my source in order to have a look here on the intensity here profile. I can just reset this to a 2D plot. It's maybe more easy to understand. And here's wavefront. When you are here, there is an important diagnostic you can do. It's Zenki. So it's very easy to change to Zenki Projection here. I just switch to Zenki. As you see, I didn't set a mask or change configuration of everything. I just put software in Zenki, and you have a circle which is now displayed and which automatically detects the largest round pupil around your available data. If you change the iris size, the software automatically detects the circle and calculates the Zenki on the exact beam diameter, your exact beam diameter. Okay, as you see, even if I decenter the lens, the software follows the beam without changing anything. And now the Zenki coefficient can be displayed this way. Here they are. You can just increase a bit the size of this window. So you have here astigmatism, coma, spherical aberration here. If I do on purpose misalignment, I can create, as you see now, astigmatism, which is quite easy to see in the Zenki coefficient here. The astigmatism at 0 degree, which is correlated with the apparition of a coma here, quite clear on the wavefront, which is displayed here. And in that configuration, for instance, you can just calculate the point spread function, which appear here, and the point spread function in live. Yeah, we are quite live here still. You can just try to increase window size and just zoom here on the. And here, if I just change the lens in order to align it, as you see, the point spread function goes to a narrow disk, narrow spot, for sure, because the aberration is now very small. And if I just do this, I can increase the aberration and add aberration in the beam, which of course create point spread function with now a lot of defects. Here's the beam. If I now want to put my finger in the beam and remove some data, oh, sorry for that, as you see, it's quite solid. The round circle is still detected, even if my pupil shape is not perfectly round. So this is quite, we improve a lot in this software, the easy to use. We focus a lot on the easy to use feature in order to help our customer to do wavefront measurement and not to think about how must I do the wavefront measurement. Just do it.
So it's all about user experience and making things a lot easier for people who have to do repeat measurements on various configurations. But it also means that if I'm correct, you've added a lens, you've aligned it, and then if you want to add another lens, how does it work?
Oh yeah, it's very easy because here I added a lens in the bench. I can just optimize its position by removing the aberration. Okay, this is quite aligned now. I know that the residual aberration is lower than 10 or 12, 13 nanometers. It's now easy just to put the sensor far from the source, let's say here, and then add another lens and just do the same. In fact, if you imagine this work, you can think that this wavefront sensor is like an oscilloscope for an optics engineer. For electronic, as a guy who want to understand what happened on his board, just switch on an oscilloscope, pick his pins and try to measure and understand things. This is the same here, but for optics engineers. You have a beam, you don't understand why your experiment is not working well. Maybe you have some aberration, maybe you were wrong when you mount a lens, maybe it's reversed. You want to see if there is spherical aberration, just drag your wavefront sensor, put it in the beam, and just do the measurement, as I just did here. Okay, no, this is not this lens. This lens is perfect. I don't have any aberration. Let's put it on another part of my beam, and that's the same. Like an oscilloscope for optics engineer, as I said.
So that's the easy part on the hardware. You don't have to bear in mind all the alignment requirements, mask, and everything. And then there's the ease of use and the user experience on software with all these very handy functions and personalized configuration that you can save and retrieve. Any other specific
I can show you. Yes, I can show you. We wanted to add in this release. Imagine that you have Wavefront acquired live coming from your beam, and you're interested to look at what you saved yesterday. For instance, let's say let's open this file here. You just double click on the HAS file, and it opens a new instance of Waveview. So you have here the live wavefront measurement of Waveview connected to the hardware, and another instance showing you a measurement obtained yesterday. And here this file was acquired a week ago on a telescope. So you can see that the wavefront sensor was just set at the focal plane of the telescope, and the telescope was aiming a star. And we measured wavefront of the telescope. As you see, the telescope is not perfectly aligned. It's quite clear that on this measurement, the Zenki decomposition shows that there's still astigmatism, coma. So something has to be done on this telescope, and some guys will go this weekend to align the telescope based on the wavefront measurement. And the guy just sent me this file just to check that everything was okay during this measurement.
So next time he does a measurement, he can bring back this instance and compare.
Exactly.
And decide whether the improvement is satisfying or not.
Exactly. Okay. That's an interesting feature about Waveview. Another thing you can imagine, if you have many wavefront sensors connected to your computer, you can have live 2, 3, 4 wavefront sensors. You have to maybe add a lot of screens around you, but you can imagine 4 live wavefront sensors connected at the same time on the same PC.
So you can monitor different beam lines at the same time.
Yeah.
Very cool. And this you mentioned telescopes, but with lasers alignment.
Yeah, for lasers we have many customers who want to measure wavefront on lasers. So on continuous wave laser, the problem is quite the same than in metrology. You just have to put the sensor and to measure. For pulse laser, there is a very simple thing here on the sensor. I can just stop here the acquisition to show you on the camera. I think it's still live, yes. There is a connector, the rear part of this sensor. So you can easily just send a TTL signal on it, like a BNC connector, and just send pulses in order to synchronize the laser to the sensor. So in this configuration, it's completely transparent here. You just have to set up the sensor in a way, here trigger mode, falling edge, rising edge, and then if I set up this, the sensor will wait for the trigger to acquire the image. So you have a synchronous acquisition of the wavefront depending on the laser pulse frequency.
Excellent. Well, thank you, Guillaume. So any other aspects you would add at this point? We're nearing the end of the webinar, and it probably would be a good time for our attendees to post questions.
Yeah, I can show you some things because we had some questions, some customers very interested in the fact to see here, if I just come back to my experiment and add an aberration to my beam here, so I can just have here the point spread function displayed with astigmatism and chroma. As here you can filter aberrations, and now filter apply on all the diagnostic windows. You can just unclick astigmatism for chroma in order to remove the effect of the aberration on the calculated point spread function. For instance, to know before the system is aligned what will be the best quality of your optical system.
Thank you, Guillaume. Jerome, do you have a question?
No, not really. I think we covered most of the important and interesting point about the features. I cannot find really a question.
Thank you. I don't see any questions either in the Q&A. So maybe if there are questions, it would definitely be a good time to address them. Otherwise, we're going to move to the summary of this presentation. And thanks again, Guillaume. No question.
Yes, we have a question from Jeremy.
Oh.
Is subtraction of background simple? Yeah, I can show you this very easily. Subtraction of background can be done here in Hartman-Graham section. You just have to subtract dark. So you can just subtract from a file. So for instance, you can hide the beam, save an image, and just subtract this image from all the future images acquired. So this is a standard way to remove a background or dark. We add also in this release new feature because we have a way to remove automatically a dark. In some conditions, it can be very easy not to save the image and then subtract it, but to automatically remove the dark pattern. So you have here a function to do this. So now the dark subtraction is even more simpler than it was before, and you have more function about this feature.
Well, thanks, Guillaume. I hope this answers your question, Jeremy. We have actually another question, but it's not really connected to this presentation. And thank you, Jerome, for handling it. And a new question.
Yeah. Can you give more information about the use of FEL? So it's a very specific question. It's a question from Naresh. Yeah, we have in our Wavefront sensor brand, Wavefront sensor dedicated to EUV light and even X-ray beam. The principle is quite the same. We don't use Hartman technology because in that kind of lens of wavelengths, there is no micro lenses, but we use Hartman masks. And the Hartman mask is very simple, and it works very well for this strand wavelengths. About Waveview 4 and hard X-rays or EUV wavefront sensor, I'm sorry, Naresh, you'll have to wait a little because Waveview 4 will be proposed to our new customers of HASO4 BroadBand since 1st of November. And as now it is written in C++ and Qt, we have many engineers able to work on this software, many software engineers. So we'll be able to add new features, to add new compatibility very fast. And we hope that in few months, we'll have this software compatible with all of our sensors, including EUV and hard X-rays wavefront sensors.
So yeah, for the next few months, Waveview 4 will be embedded only with our new HASO hardware. So that's the HASO BroadBand and a couple of new HASOs that will be announced in the next few months. But as Guillaume mentioned, we are working on providing compatibility with older Wavefront sensors, and we will release the information as soon as they become available. The overall idea is we would like to see most of these HASO migrate to Waveview 4 probably before summer next year. So thank you for your questions, both Jeremy and Resh. I hope you enjoyed this webinar, and just to summarize what we've seen today with Guillaume, we'll go back to the presentation and the summary of what we've seen. So Guillaume has used the new HASO4 BroadBand, which is broadband and magnetic, and embeds this new SpotTracker feature that's allowed also with the use of Waveview 4. We've demonstrated some of the new features, and you've brilliantly illustrated the new layout, which shows a significant difference from previous ones. But as you mentioned, the most revolutionary aspect is the language and the way it was developed. Part of the layout is the ability to create and save custom configurations, but we also so that it was possible to open many different instances in parallel, including saved measurements or other live measurements. So SpotTracker is definitely a functionality you should think of if you're working in aligning lasers, in metrology, and aligning telescopes also, as you mentioned. And lastly, we also covered the fact that our SDK is now offered in 4 languages, including Python. Well, thanks much to everyone, Jerome and Guillaume. Our next webinar will be on November 17th, and it will focus on Square with a brand new HASO Square that will also operate with Waveview 4, and an RFlex and LA Square, just like the one we showcased in our previous webinar in June. That's still accessible on our YouTube channel as discussed before. So stay tuned and stay safe. Thanks again, and it's now time to, oops, sorry about that.
Say final hello. Yeah, final.
It's now time to say goodbye. Take care.
Goodbye.
Bye-bye.